Hello everyone, this is Daniel Smiley on behalf of Ozen Engineering Corporation. I'm going to talk about modeling battery and calculating model parameters. In this presentation, we're going to cover a model, electrical model as shown here, and results of tests where the author were able to calculate the value of the element in this model. This presentation is based on an IEEE paper. At Ozen Engineer, we solve multidisciplinary engineering problems, and we have different expertise from FEA, CFD, all the way to high frequency and low frequency electromagnetics. It's also good to point that we are a light channel partner of ANSYS. So in this presentation, I'm going to talk about LCV and SOC, the basics, and then I'll talk about charge and discharge profile, followed by battery picture. Then I talk about the current profile and how OCV is based on SOC, and then the resistor calculation. So the very basic, let's talk about the SOC, which is the state of charge, and also about OCV, because these are two parameters that are important for making a model on the batteries. Here you'll see the scientific definition, and on the right hand side you see an icon. Almost all of us have seen this on our laptop, tablets, smart devices, phone, etc. So basically it means how much power is left in your battery. After looking at SOC, let's take a look at OCV, which is open circuit voltage. So let's take a look at a very traditional battery. If you have one battery here, and please note it's open circuit, so there's no load connected here on this side. If you put the meters and across the battery, you read 1.5 voltage, which is the terminal voltage. Here, the ideal battery is also 1.5 voltage. When you connect a load, in this case 8 ohm, you'll see a drop in the voltage. The reason is that there is an internal resistance in the battery. So here is the ideal one, and here's the resistor which makes the real battery in real life. And then there is a drop in the voltage in the internal resistor. That is why you will see 1.33 volt at the terminal. So terminal and open circuit voltage are always different unless there is no load connected to the battery and the battery is rested for a long time. Now that we know OCV and SOC, let's take a look at the model. So here it's very similar to the battery that I showed you, the ideal voltage source along with the internal battery. The point is that the internal battery is a function of SOC, so it means it's not constant. OCV is also a function of SOC. And it's also good to point that on top of SOC, temperatures are also a big factor. However, in this test, temperature will remain constant, so it's just based on the SOC. You'll see the OCV and are internal here. However, something is missing here. If you look at like around yourself, you'll notice that there are many cases where you left the battery and the battery died after a long time. This model doesn't represent that. In order to do that, we need to add another item, which is self-discharge. So basically, if you leave the battery for a long time through this resistor, the battery starts discharging and loses its energy, and eventually it becomes dead. Now that we know the battery model, let's take a look at the test. On this test, the author did it in two different phases. One is charging, one is discharging. Here it was charged for 1 minute. It was rested for 10 seconds. Again, charged for 1 minute, rest for 10 seconds. That is why you see these two here. Same here. It was discharged at 80 amp, Reset for 10 seconds, again discharge. At 80 amp, reset for 10 seconds, discharge for 1 minute, and keep going on till this point, where there was no juice left in the battery to discharge it with 80 amp. That is why the test was changed to 30 amp instead of 80 amp. And that's where you see this peak going up again and come back down all the way here. And once you reach this point, you can no longer take out 30 amp from the battery. It's just not enough power there. However, the SOC is not zero, means we didn't kill the battery all the way. In order to do that, the resistor was connected to the battery. That's why you see this jump here. So it goes up and the resistor is there, and we give it time. So after a while, there is no current at all in the circuit, and means the SOC goes all the way to zero. Here is the battery, how it looks like, and its pump, reservoir, and stacks. The size of the battery is equivalent to a vending machine. The test was done on these batteries. Now that we see the battery and the voltage profile, let me show you the current profile. So this is the voltage profile that was shown. And this side is in the current profile. So it was discharging, it was charging here. Here we got it discharged at 80 amp, and then it was discharged here at 30 amp, and then it was discharged with the resistor. Same thing was applied with 150 amp. That is what you see, 150 here, whereas 80 here. And again, same here, it was discharged at 30 amp, it's discharged here at 30 amp too, and then the resistor is connected to it. This test was done at different amps, and the terminal voltage and OCV were measured at different point. So, long story short, if you plot OCV based on SOC on different current, this is how it looks like. As you can see, they're all converged here, means no matter what the current is, OCV has same behavior. There are some, you don't see a convergence here. The reason is that the battery was not rest for a long time. If the battery was rest for much longer than 10 seconds, these points will eventually converge too. So now that we have all these points, we try to fit a curve on it, which is this yellow line. And then if you match a formula on it, this is what you will get. As you can see, this is the OCV based on SOC. Next is about internal resistance. It's just the basic formula, R multiply I equal to delta V. So delta V over I will be R. And what is delta V? It's just open circuit voltage near the terminal voltage. We have all this data, so we can calculate the internal resistance. And as you can see, it will give us this profile. Again, you see convergence here, and the data are scattered at this point. It's the same reason the battery was not rest for a long time. If you now that we have different points, we can fit a curve to the internal resistance, and the only part that is left is self-discharge. For self-discharge, there is also a curve, but the author decided to have a constant number for it, not a function. The number was 5.121. So we have the self-discharge here from the test. We have the internal resistance, and we have the open circuit voltage, and the model is completed with all these numbers, and we have it based on SOC. Again, it is only based on SOC, and the temperature is not involved here, and the temperature was remained constant across the whole test. And it's good to note that it takes a long time to capture all these data, and each current, for instance, 300 was measured twice to make sure everything is constant and on the same behavior. So the battery is modeled here. We have the parameters, and we can use that for analyzing the circuit. Hopefully this gives you good information. If you have any question, please do not hesitate to reach to us. Or if you need a design or a consultant for your product, please also feel free to reach to us. You can reach us at info@ozen.com. If you don't like email, you can call us, or you can go to our website, ozeninc.com, and see all the products and services that we provide. Have a great day. Again, this is Daniel Smiley from Ozen Engineering Incorporation.